So let me just briefly summarize and tell you the sort of points to the important contributions that Turing made in this paper on computable numbers. There are sort of three broad areas. One is that Turing's proof of the undecidability of the decision problem is an important part of the history of logic, or one of the fundamental theorems in mathematical logic, and shows the limitations of logic and the axiomatic method. His invention of the Turing machine model of computation is one of the foundations of computer science, or at least theoretical computer science. The idea of the universal Turing machine, sort of one of the origins of the stored program computer, and the idea that you can have a program which runs other programs on a given input, that you don't have to hardwire your computers, that you can just write the program onto its tape, so to speak. And then the analysis of computation that is given by the very model of a Turing machine. So the first one, right, that logic cannot be fully mechanized, of course, is an important limiting result in logic. The decision problem is unsolvable. Historically, it of course had an impact, right? Because it was surprising. People thought that, sort of expected that the decision problem could be solved. And despite the fact that it was solved in the negative, people still, there was a sort of the fact that now we have these examples of unsolvable problems, right? Resulted in a huge industry of mathematical logicians investigating certain specific problems, right? So the general problem that you could solve everything with one Turing machine, that was unsolvable, but perhaps you could come up with a Turing machine that tells you whether something is a theorem of geometry or of the theory of real numbers and so on, right? So that was one of the important benefits of coming up with some examples of unsolvable problems. In computer science, of course, the whole theory of Turing machines and the kinds of functions that can be computed by Turing machines became a branch of mathematics called recursion theory. And once computer science sort of became its own discipline, it sort of almost turned into, or was subsumed under theoretical computer science, and now Turing machines, of course, are the model of computation that theoretical computer scientists use, for instance, when they're interested in whether something can be, what the complexity of certain procedures is, or the complexity of certain problems. The standard way of modeling that is to say, well, is there a Turing machine that runs in so and so many steps, or uses that amount of space on its tape as measures of the complexity of a problem in terms of the time required to compute it or the space required to compute it. And then lastly, sort of conceptual philosophical payoff. What I haven't talked about this, but I mentioned that briefly mentioned that Turing had a number of sort of conceptual reflections in his paper about what would show that his model of Turing of computability by Turing machine, captures everything that could conceivably be computed. And he had sort of three arguments. The first argument was sort of, well, let's reflect on what we mean by computing, right? When we talk about computing, we sort of, or like, I guess in 1936, right, before there were computers, right? When people were talking about computing, they were talking about, things that you do with a pencil and paper, using a certain definite procedure, right? And Turing reflected on, what happens when people do that, right? They change the symbols that they write on the paper and so on, and argued that the Turing machine doesn't do anything other than what's happening there, right? Then the second argument involved proving the equivalence of Turing machines with other proposals for the analyses of the notion of computability. There were, at the time that Turing was writing, there were two. There was one due to Gödel from 1934, the notion of general recursivity, and then the second one was due to Church and his students, Kleene and Rosser, the notion of lambda definability. And in an appendix to that very paper, Turing proved that Turing machines can compute exactly the lambda definable functions. So it was one of the first examples of showing that Turing machines compute exactly what some other possibly proposed notion of computability does. And since then, there have been literally hundreds of proposals for extensions of Turing machines. You know, let's just not use one tape, but two tapes, or infinitely many tapes, or all kinds of other things. Multiple read-write heads that can operate on all kinds of things in parallel. All of these things do the same thing as the very simple Turing machines that we do, that we've looked at, right? And then, of course, everything that you can compute in the various programming languages that computer science has developed, everything can be simulated by Turing machines, right? And that's another reason for why people think that Turing machines just capture what it is to be computable. And then the third one was showing that, well, Turing machines actually compute lots of things, right? So the two examples that we've looked at were very simple, right? And perhaps just by looking at them, if you didn't know Turing machines, right, or didn't know the fact that they can compute anything that you can compute in C, for instance, or Prolog or Lisp, then perhaps you wouldn't believe that they can compute all kinds of numbers, that it can compute all kinds of number theoretic functions and so on. And in the third part of that section, Turing argued that they can actually compute many things. Okay? So these three sorts of reasons were the kinds of reasons that people were then persuaded people to accept Turing's solution, negative solution of the decision problem, to be definitive, right? Because if you didn't think that, right, so what Turing showed, but also what Church showed, was that a certain type of way of computing things isn't strong enough to solve the decision problem, right? But that would leave open the possibility that, well, perhaps there is something stronger, some stronger notion of computability which could solve it, right? And it's these kinds of considerations that convinced people that there couldn't be any stronger ways of computing things which would solve the decision problem. And that is that thesis that what's computable by a Turing machine is what's computable, period, is now known as the Church-Turing thesis, because first proposed by both Church and Turing. And that is all I wanted to tell you today. Thank you.